Hey, here we're going to take up assessment number 2, but I've broken this down into 2 parts to make this one a little bit more focused for those of you who need it. Part 1's just going to focus on the questions that were based on similar shapes. So if you feel comfortable with similar shapes now and you're sure you don't need this, you can go on to part 2. But those of you who need this, and I know there are quite a few of you, I have 2 other videos posted already about similar shapes, but hopefully this one will help as well to help clear this up. Right, so the 2 similar shape type questions on this assessment was this one here, where we're talking about 2 solid coins that are mathematically similar. So they've told us that they're similar. You've got the volume of one, you've got the volume of other, and using that knowledge, you need to work out a simplified ratio for the surface area of one to the surface area of the other. The other similar shape question on this paper was this one, which really should be pretty straightforward. If this is not easy for you, you need to stick with this video and you need to make sure that it is easy for you so that on subsequent assessments you don't have any problem with something like this. Okay, let's get started. So with a little bit of background with similar shapes, starting with a similar square. 2 squares will always be similar regardless of their size because squares by definition have the same length on all 4 sides. So if I were to double the length on one side, I'm doubling the length on all of the sides. If I were to half the length, I'd be halving the length on all sides. So squares by definition are always similar. So these 2 squares are similar. I've told you firsthand that this is a square. This has got a side length of 2 centimeters. This has got a side length of 4 centimeters. You could probably easily work out what the scale factor is, what this was multiplied to make that. But the trouble with similarities is that you're not quite understanding that the scale factor for length is not the same as the scale factor for area and for volume. So looking at the lengths, these are one-dimensional measures, just a straight line. I'm not using a square to fill an area, that's a 2-dimensional measure, nor am I using cubes to fill a volume, a 3-dimensional measure. It's just a one-dimensional length. So when we're looking at one-dimensional lengths, we're trying to find the scale factor, and it's just the scale factor, not squared or cubed, just the scale factor that links one length to the other. If I got the side length of A is 4, the side length of B is 2, I could say that the side length of A is equal to the side length of B multiplied by some number, some scale factor. That's the number that makes the enlargement, or if it's been made smaller, it's still called an enlargement, but it might be a fractional value. Now I set it up this way on purpose because I wanted to work with a whole number scale factor, not to confuse you any more than you already are by having a negative or a decimal or a fraction scale factor. So I've said that length A, which is the longer one, is length B, the shorter one, multiplied by some number. So that would be a number that's bigger than 0 point something, a number bigger than 1, to get the scale factor. Okay, length A is equal to length B times 2. Now, if you didn't know that, you could have done length A 4 divided by length B 2 and get your scale factor that way, just rearranging this. But I think this one was pretty clear and straightforward. My scale factor is 2. But that means that also the perimeter of A, so adding up all of those sides, is equal to the perimeter of B, adding up all those sides, just times by 2. Because perimeter is also a one-dimensional measure. It's a sum of lengths, but it's just adding together those lengths. It's not a 2-dimensional measure, and we're not filling a space. Okay? When we look at the areas, however, the areas are 2-dimensional measures. That's why when we measure areas, we measure them in centimeters squared, little 2 there, or meters squared, or kilometers squared. That little 2 up there stands for the number of dimensions that you're measuring with that unit. Okay? So if I say that the area of square A is 16, which it would be, 4 times 4, and the area of B is 4, which is 2 times 2, centimeters squared in both cases, squared units of measure because this is a 2-dimensional measure, then I would say that the area of A is equal to the area of B multiplied by a scale factor squared. Now I already worked out what the scale factor is. That links 4 to 2. My scale factor is that I doubled the 2, I times by 2. Now, if you work out the area of this square, though, which is 16, it is not twice the area of that one, which is 4, because I have multiplied the length by 2 to make it 4, and I've multiplied the width by 2 as well to make it 4. So that means that I've multiplied by the scale factor, I've multiplied by 2 in 2 different dimensions. So I've multiplied by the scale factor twice. That's multiplying by the scale factor, multiplying by the scale factor again. That's the multiplying by the scale factor squared. Okay, so that means that area of A is equal to area of B times 2 squared. The scale factor is still 2, the same scale factor as I had for the lengths, but for the areas, I multiply by that scale factor squared. So to find the area of A, I have to multiply the area of B by 4, because the scale factor squared is 4. Okay? Now, if I want to talk about three-dimensional measures, I can't be talking about squares because they're only two-dimensional. So I'm looking at similar cubes now. Using the same values, the same measurements, this side length is 4 while that side length is 2. And I could say that the side length of this is equal to the side length of this multiplied by some scale factor. I can see that 2 got doubled to make 4, so my scale factor is 2. But the area of this square, 4 times 4 is 16, is equal to this area, not times the scale factor, but times the scale factor squared, times 4. That area is 16, which is the same thing as this area, which is 4, times 4. The surface area, similar to what we said about lengths and perimeters, they're one-dimensional measures. Surface area is another two-dimensional area because it's the sum of all of these areas. Sorry, surface area is a two-dimensional measure. So for the surface area of this smaller cube, I've got an area of 4 on this face, and I've got 6 faces that are equally the same size. So that's going to be 4 times 6, that's 24. That's the total surface area of this one, 24 centimeters squared. The total surface area of that one should be equal to the surface area of this one multiplied by the scale factor squared. The scale factor squared would be 2 squared. So if this has got a surface area of 24, this should have a surface area of 24 times 4. Go ahead and pause if you need to and work out the surface area of this one. You'll see it's the same as the surface area of this one, multiplied by the scale factor squared. That's multiplying by 2 squared, which is multiplying by 4. Now we're going to move on to the volume. Doing the practice to making sure you've got the clear idea of this is up to you now. Going on to the volumes though, it's a three-dimensional measure. So if I can find the volume of this cube, that's 2 by 2 by 2. If I multiply that volume by the scale factor cube, because I need to multiply this 2 by 2 to get that length, I need to multiply this 2 by the scale factor to get that length, and I need to multiply this by the scale factor to get that length. I'm multiplying the scale factor in 3 different dimensions. I'm multiplying by the scale factor, multiplying the scale factor again, and multiplying by the scale factor again. That's multiplying by the scale factor cubed. Okay, so the volume of A is equal to the volume of B multiplied by the scale factor cubed. In this example here, remember our scale factor is 2. Go ahead and try it for yourself. You can find the volume of this cube, 2 by 2 by 2. And you can find the volume of this cube, which is 4 by 4 by 4. And you should see that this volume is equal to this volume multiplied by our scale factor cubed. So that's multiplying by 2 cubed. Remember, that's 2 times 2 times 2. That's 8, not 6. Okay, try it for yourself. Put this on pause if you need to. Learning that, understanding that, and getting the practice, that's up to you now. Right, so on to this question now. Similar spheres. Sorry, this is not a question from the assessment, but are coming back to how squares will always be similar, cubes will always be similar. Rectangles will not always be similar because you've got 2 different measures there and you need to make sure you maintain that same proportion, right? But spheres will always be similar in the same way that squares are always similar because the radius of a sphere is the one measurement that we judge a sphere by. This sphere has got a radius of 3. That's in all different directions here. If the radius is 3, the diameter is 6. But just knowing the radius, I know that this is a sphere, and I know that this one with a radius of 1 is 1/3 the size of that one. I don't need any other measurements to tell me that this sphere is 1/3 the size of that one. Or to make things easier for you, I would say that this sphere is 3 times the radius of this sphere. Okay? So, thinking one-dimensionally again when we're talking about our radiuses, The radius of A, so the bigger one, is equal to the radius of B times some scale factor. Again, I could have put it the other way around for you, but I'm trying to keep this simple, making that scale factor clear and obviously the whole number 3. If I times this radius of 1 by the scale factor 3, I get the radius of 3. Same thing with the diameter. This diameter here, as we know, would be double the radius. Double of 3 is 6. That's the same thing as this diameter multiplied by our scale factor. And we worked out our scale factor before. Our scale factor was 3. So if this is a radius of 1 times 2 is 2, 2 times the scale factor gives me this diameter, which is 3. Again, that's one-dimensional. You shouldn't have any problems with that. When we get into 2 and 3-dimensional, though, that's where you're going to need to do the practice. So the volume of this 3-dimensional shape, the volume of these spheres, they need to follow the rule that I need to multiply by the scale factor, in 3 dimensions, length, width, and height, right? So that means multiply by the scale factor cubed. The volume of A is equal to the volume of B multiplied by the scale factor cubed. Now we've already worked out what the scale factor was. The scale factor was 3, so this volume is equal to this volume multiplied by 3 cubed. Oops, I've got a little bit backwards here. And the surface area of this one is equal to this surface area multiplied by the scale factor, which we said was 3, squared. Right, now you've got some time to work that out. You know the formulas for these things. For the lengths, it's straightforward. That has been multiplied by 3, so my scale factor is 3. My scale factor squared to help me find the area, 3 squared is 9. And my scale factor cubed to work out my volumes, 3 cubed is 27. Here you've got your formulas to work out the surface area of both of those spheres. Notice that this sphere will be 9 times the surface area of this sphere. And notice that the volume, use these formulas to work out your volumes. Notice that this volume is 27 times the volume of this volume because of the scale factor cubed. Again, you need to do the practice. You need to make sure that you understand concretely by doing it for yourself. So go ahead and give that a try. Right, hit pause if you need to, otherwise let's keep going. On to this one now. Now this should be really simple and straightforward. You know how to convert between metric units of length. 1 meter is 100 centimeters. So converting from meters to centimeters, we times by 100. But going back to what we were saying about one-dimensional measures compared with two-dimensional measures and three-dimensional measures, well, this is a three-dimensional measure. I'm converting 2 meters cubed into centimeters cubed. So I need to multiply by the scale factor cubed. Okay? If I were working out centimeters squared to meters squared to centimeters squared, I would multiply by 100 squared. Now that I'm converting from cubed to cubed volumes, I'm going to multiply by 100 cubed. That's multiplying by 100 times 100 times 100. That's multiplying by 1,000,000. That's going to be 2 million. No, when I multiply by 100, I add 2 zeros. If I'm going to multiply by 100 3 times, 2 zeros, 2 more zeros, 2 more zeros. Should have been simple. That was meant to be an easy mark for you. So I'm hoping if it comes up on the next assessment, it will be an easy mark for you. Here's some more metric conversions to consider. So I don't want you to think that's only with centimeters and meters. You know how to convert between millimeters and centimeters. We divide by 10. So to convert between millimeters and centimeters squared, we divide by 10 squared. Millimeters cubed to centimeters cubed, we divide by 10 cubed. That's 1,000, that's 100, just to be clear. Right? And going between kilometers and meters, to get from kilometers to meters, we times by 1,000. From kilometers cubed to meters cubed, we times by, squared to squared, we times by 1,000 squared, that's 1,000,000. And kilometers cubed to meters cubed, we multiplied by 1,000 cubed, so that's 1,000,000,000, 9 zeros. Okay, we don't need to go through all of the conversions. The idea is there. One-dimensional, use the normal conversion. Two-dimensional, use that conversion squared. Three-dimensional, use that conversion cubed. Okay, this next one. Two solid cones are mathematically similar. Cone A has a volume of 120, cone B has a volume of 960. Work out the simplified ratio of the surface area of cone A to the surface area of cone B. Okay, so we're talking about volumes here, and here we're talking about surface areas. First of all, let me make one thing clear. Unlike spheres and squares, cones are not always similar. This example here just goes to show that. The base here looks like it's even gotten bigger on that one, but the height's gotten smaller. So this is not an enlargement of that one. Okay, so they're not always similar, but they need to tell us it's similar, or we would have to work it out for ourselves. Okay, cones are not always similar. We must be told they are similar, or work it out by comparing both the radius and the height, or both the radius and the length. I need to use both of those measures to make sure that one hasn't been doubled and the other has been tripled or something. Okay, but coming back to this example, these two cones look more similar. The base has been enlarged, the height has been enlarged, and they must have been enlarged by the same scale factor for them to be similar. But we need to just use similar shapes to do this. Otherwise, you're going to lose a lot of time working out what the surface areas are, and we don't even have enough information to work out what those surface areas are. So let's get started. If these volumes are three-dimensional measures, one volume is some multiple of the other, but multiplied by the scale factor cubed. So to make this easy on you, I'm going to say that B is the same thing as A multiplied by some scale factor cubed, right? Because B is the bigger one. So volume B is equal to volume A multiplied by the scale factor cubed, because this is a volume, three-dimensional measure, cubed. Let's work out what the scale factor cubed is. I know what volume B is, it's 960. That must be equal to volume A, which is 120, multiplied by some scale factor cubed. Okay, just for simplicity's sake, I put SF instead of the full word scale factor. Okay, should be really easy to rearrange that. I want to know what the scale factor is, so I move the 120 to the other side. Okay, and now I want to know what the scale factor is. That's the scale factor cubed. I want to know what the scale factor is. So it's the cube root of this answer. Cube root of 8 works out really nicely for me, is 2. That means that whatever this radius was, it was doubled to make this radius. Whatever this height was, it was doubled to make this height. My scale factor is 2, which is why my volume is not just 2 times the size, but 2 times 2 times 2 is 8 times the size. Okay, so that given, I can now set up a ratio for the surface area of cone A to the surface area of cone B. I'm going to start by writing that ratio just in words. There you go, surface area of A to surface area of B. Now, I want to replace these words with numbers somehow. Even though I don't know what the surface area of A is or what the surface area of B is, I do know that the surface area of B is equal to the surface area of A multiplied by the scale factor squared. And the scale factor squared is a number I can work out. Scale factor is 2, so the scale factor squared must be 2 squared. So I'm going to go ahead and substitute that in here. Surface area of A, 2, surface area of A times scale factor squared, right? If anybody's lost, this is taken directly from this down here, the definition of similar shapes. One surface area is equal to the other surface area times the scale factor squared. Now, I got a number here. The scale factor squared will be 2 squared, which is 4. I still have these words instead of numbers, but I know that to simplify a ratio, I need to divide both sides by the same value, and I've got the same common factor on both sides here. I can divide this side by the surface area of A. I can divide this side by the surface area of A, and that leaves me with 1 to 4. So it's a lot of thinking, but not actually a lot of calculating or a lot of work done there, right?